I would like to talk about why linear regression is not a good choice for method validation. The back reason is regression to the mean, which is a well-known phenomena in regression. And well, this is my copyright. Just to have a quick review, remember classic linear regression. You have some points, you have a line which is the best line for those points. Usually for classic linear regression we set a test null hypothesis which we hope to reject, and this null hypothesis is that the slope is 0 and the intercept is, well, whatever is something or nothing. This is pretty much open to the complexity of the experiment, if you have more independent descriptors or not. But you are testing against a slope equal to 0, and this is the point. The point is, if you have a small variation of this slope, it won't make that much because you are confronting against a 0 value. If you do that for method validation and you try to use linear regression, you might think that it is the same, but it's not the same. It's really not the same, and you really you have to use it, because you have some points. You have this line which is black in this case, just a matter of taste the color. But what really matters is the test, and what is your null hypothesis. The null hypothesis is that the slope is 1, because you expect that the validation is such that the two instruments or the two different methods of measurement, they should measure the same thing, and so your expectation is very clear, is 1, okay, and the intercept is 0. So we have also a strong statement about the intercept, what in this case is not. And the third point is we try to confirm this null hypothesis instead of rejecting it, which is a bit the evil of statistic. But to make this confirmation, we need some precise statement about the confidence intervals of the measured slope, which might be very sensible to the fact that we have some regression to the mean. This means that if the data is dispersed, the slope tends to be slightly weaker than what it is expected, and then we have already a significant difference. I remind you that with high correlation, the line will follow the points pretty precisely, but with lower correlation, if you use a classical linear regression, the obtained line, the slope of the line, will tend to 0. This is just how classical linear regression works, and this means that if you have something in the middle here with some dispersion, this slope tends to be a little bit weaker than what it should be, and this is the problem, because we are testing against slope 1 and not against slope 0. So we need a very precise determination of the slope, which cannot tolerate this effect of reducing the slope given by the dispersion of the data. So going to my RStudio, part of this work is already published on arXiv in 2021. You have the link here. There is some more new material which I've put out on my GitHub scientific blog, but basically this is I will use this data generating function, which is already described in 2021 publication, and this is simply a function which generates a data set, and I'm using a set seed, so you can reproduce exactly the data I'm working on. So this is a kind of model. We have 100 samples which have been randomly collected, and we have two measurements, x and y, and actually these points should really lie on, this is the identity line, on the identity line, because they are originating from the entity line, and then an error component has been added both for the x and the y component, so that they are not really all sitting on the line, but they are spread around this line. Okay, and this is the very ideal identity line. It is the originating line. The model is such that the data is originated by this line. We know in advance because we have done it. Now if we run a linear model with this command, and then automatically we extract and print the line, we see that this blue line, which is the regression line, is slightly lower than what we would expect, and this is exactly what I was talking about, regression to the mean. Of course this is only one sample, and somebody would say, hey, but this is only one sample, it could be even higher or lower, and it could be statistically distributed. But yes, it is exactly what we are discussing today. I can, yes, of course, put a legend, but let's say we do just 6 models of them, or repeating, just we just generate a new data set and then we do the regression again. I have put everything in this function, so I can call the function. I just put 2 by 3 graphical output, and I just execute 6 regressions, and you see from these 6 regressions that basically the blue line is lying at a lower value. Here is more, for example, evident on this side. Okay, it's less than 1. Here is clearly less than 1. Here is probably a little bit more near to 1, but here again is less than 1. Here is, you see it, less than 1, and here too. So in all these screens basically we have a slope which is slightly less than 1. But again, these are only 6 cases, and probably you are not happy with that. I'm not happy too. So let's say now I just build a very large matrix with 10,000 datasets, and for each of this dataset I generate a new dataset, and then I extract just the coefficients. And this is pretty straightforward to do it. It takes several seconds, but it's not so terrible to do it. Should be, at least. Yes, we got it. And now what I do is just to split this graphical output in 2, and I plot 2 kernel densities, one for the slope and the other one for the intercept. Watch now what happens. This is the kernel density plot for the slope. You might see, okay, this is more or less what I would expect, but as you see, our ideal slope is 1, is not centered, and to see it better we just draw where it should be, and you see that the value of the slope is systematically somehow lower than what we would expect, because we know that we have generated all these data sets at slope equal to 1, so we expect that 1 should be on the tip of this distribution, but it's not. Indeed, if you take, for example, the mean, you see the mean is positioned at something like 0.98. And we can do the same with the intercept. You see the intercept is also shifted. So what we would expect is 0, but actually it's a little bit more. But this is clear. If the slope is weaker, it automatically makes so that also the intercept get a little bit elevated. So the intercept is a bit higher than 0. About this is our expectation, and this is the reality. and this is again our expectation. So this makes people not happy. Why? And this is really why you should never use linear regression for method comparison. Okay. Now it's also interesting to see what happens if you take a larger variance. So if the points are more spread out, not like this but more spread out, we will find even a lower slope in average. And this is what I do here. I repeat the experiment with 10,000 regressions, but I take, you see in the difference, I was taking 0.2 units of dispersion, and now I take 0.5 on the same data set from 3 to 8, just like for example something like potassium or sugar in blood or something like this. We can execute, first to make the matrix ready, and then we can execute the script. Again, it takes several seconds, it's not that bad. Yes, and again, if we do the plot, you see that now our expectation value of 1 is very far from reality. We are even below 0.9. So this augmented dispersion caused a stronger shift toward 0. The slope is moving toward the 0, and of course the slope, the intercept is growing. The bigger the variance on both instruments, the stronger will be this regression to the mean effect. Okay. Now, why you should use special regression? It comes next, and this is quite easy. Of course, you cannot do it with Excel or with conventional spreadsheet systems, because these are specific regression that are usually on professional tools. But this is not a problem for error, because for example we can use the MSCR package, which allow us to calculate the Deming regression. So I load the package, I prepare a new matrix, in this case with 4 columns, because I will do this very same data set. I will test it with classical regression and with Deming regression, and for that I need a larger matrix with 2 additional columns. And again, I can call this. So for each of these loops, I just first generate a data set and then store the coefficient of the classical linear regression, and then I call mcreg, which is the main engine of this MCR package, and I do a Deming regression analytical, and I just store the slope and the intercept in the same matrix. And this takes a little bit longer, but not too much. We can just wait a second and sip from my cup of coffee. But it will be several seconds more and we get the result. Okay, it's over. So we can again, we split like this graph, just we split in 2, and we plot the kernel densities of slope and intercept. So the first part here is just about slope. This is the first plot. This is the slope with traditional linear regression. This is our expectation line. I also put a grid to read it better, and then I overlay that with the kernel density of the Deming regression, which has been stored in the column 4, and it will be pictured in red, and you see the difference. The Deming regression, actually what we have as expected value of the Deming regression for the slope is the correct one. We can also calculate the mean for the classical regression and for the Deming regression, and depict them, and you see that the mean of the classical regression is off the target, and actually that the Deming is pretty precise on the expected value. And exactly the same, I can add the legend too. Exactly the same happens with the intercept. I go a little bit quicker, but you see this is the classical regression. I add the grid, and then I add the Deming regression, which again the expected value is exactly on spot, and the two lines and the legend. So this is really the main point of the whole discussion. You should really not use linear regression to make method comparison or method validation, because you just systematically have shifted your slope to have wrong slope. You have bias basically, and you have a bias both on slope and on intercept. If you are interested, you can also listen to the very last part of this report, which is a bit it's important, but perhaps a little bit less, because you can also test the very same experiment and add to this experiment also the Passing Bablok family of regression. But to do that, since it's quite slower to do it, I just do it using library parallel, and so the script looks a little bit different. I just first write this function which generates the dataset and then makes the 4 regression one after the other, but I don't prepare a matrix. Instead I just return the row of the results, because I'm going to use parallel, and I am going to use this function which is Meckel apply, which stores the results in a list. So I just define this function and if I call it just only once, you see that this function generates a data set and then make 4 distinguished regressions. And now I just detect how many cores on my machine is 8, and I can repeat 10,000 times this script and store the results in this list, and then I will convert the list into a data frame to be more readable, and we draw the summary just by calculating the averages. And this is quite straightforward. This takes again several seconds, but it's not so terrible because we have in parallel running. Otherwise, it's quite quick, because splitting the job onto 8 processes, it's of course quicker. And I just convert the data set and name the columns, and I don't want to make again all this graphical work. It's interesting to just draw the summary of this data frame, which will be very clear. Here we are. I just call the summary, and as you see, these 2 first columns are linear regression, the intercept and the slope, and you see the intercept is quite different from 0, and you see also the minimum and the maximum, they are not symmetric, but this is not so important. The most important part is really that the mean and of course the median, they are not equal to 0, and the slope is not equal to 1. You see we get something like 0.898. With all the other methods, which are specific methods for method comparison or for method validation, You see that the intercept is pretty much around 0, and that the slope is really pretty much around 1. This is for classical Deming. This is for classical original Passing Bablok algorithm. You see the slope is about 1. This is for the equivariant passive and the new equivariant Passing Bablok. I am developing personally Bayesian Deming, which has some very interesting features, but this is not the topic of this discussion. This discussion is about why you should really not use linear regression with comparison data. And you see that all these specific methods for method comparison, they provide a pretty good estimate of the slope, and this is quite in contrast with what classical linear regression do. And that's exactly this manifestation of this regression to the mean effect. And actually the take-home message for today is never use simple regression for method validation or for method comparison. You should not do that. Use instead, for example, Deming method, or for example Passing Bablok methods. It can be hard the choice between these, and there are a lot of details. You can watch in my blog what I think about that. I just prefer Deming because Passing and Bablok has some problem about the rounding and the low precision data. If this is not a problem, so if you have a full precision data, you might also use Passing Bablok, but this is almost never the case. Or, of course, there are also other orthogonal regression methods, like principal component regressions or so on, which are probably even more difficult to use. But actually, one of these two alternatives is not a bad choice. And really, again, please do not use linear regression for method validation. Thank you.